Raw data is inherently chaotic. Sorting is the computational process of forcing that high-entropy noise into a strict, perfectly sequential order. Standard iterative algorithms approach this problem linearly, comparing one element against the rest. As the dataset grows, approaches like selection sort hit a severe bottleneck, bound by a quadratic time complexity of O of n squared. Bypassing this limit requires a different architecture. Merge sort abandons the standard iterative loop, guaranteeing an O of n log n performance across all operational cases. It achieves this speed through a structural strategy known as divide and conquer. The algorithm executes in 3 sequential phases. It blindly divides the dataset, recursively conquers the resulting subproblems, and finally merges the sorted pieces back together. Achieving faster sorting means abandoning the optimization of individual comparisons. We have to structurally alter how the algorithm handles the dataset itself. We begin with a fully unsorted 8-element array to trace the execution from the top level. The first phase is division. The algorithm calculates the exact midpoint and blindly fractures the array into 2 halves. It does not read or analyze the values. This division is recursive. The same splitting function is immediately applied to the newly created subarrays. Notice that during this downward traversal, absolutely no sorting, comparing, or logical evaluation takes place. The arrays split a final time. We are left with 8 completely isolated single-element blocks. This is the mathematical base case. An array containing exactly one element requires 0 computational logic to sort, because it is impossible for a single item to be out of order. By recursively halving the array, we have fragmented the original problem into 8 trivial subproblems, creating necessary conditions for the merge phase to begin reconstruction. With the base cases established, the bottom-up phase begins. We focus on merging 2 already sorted subarrays using a 2-pointer technique. Combining them requires a strict memory allocation. A new temporary array must be instantiated to hold the incoming sorted elements. Pointers I and j initialize at the 0 index of their respective subarrays. The logic evaluates the values at both pointers, identifies the smaller integer, and drops it into the temporary array. Comparing 3 and 2, the 2 drops down. The pointer tied to the winning value increments by 1 space. The losing pointer remains stationary. In the second iteration, the loop compares 3 and 4. 3 wins, drops down, and pointer I moves to the right. This sequential loop fires continuously until all elements from both the left and right arrays are completely exhausted. Because every single element across both arrays is evaluated and moved exactly once, this merge operation costs exactly O of n time. Merge sort is fast because all the computational heavy lifting is isolated to this linear loop, but that speed is explicitly purchased at the cost of O of n extra spatial memory to hold the temporary arrays. We can map these physical actions to standard algorithmic notation. The main function calculates the midpoint, recursively calls itself on the left half, and then the right half, driving that downward fracturing. This strict sequence introduces a critical edge case, how the algorithm handles identical duplicate values. Consider 2 identical integers, tagged here with hidden metadata to track their movement. The standard merge operation uses a less than or equal to comparison. When a tie occurs, the logic structurally favors the element originating from the left array, moving it down first. In computer science, preserving the relative input order for duplicate elements is called stability. Merge sort's Kiebreaker logic guarantees a stable sort. We can model the algorithm's complete computational footprint by defining its recurrence relation. The term 2Tn/2 represents the 2 recursive subproblems, while the plus n captures the linear time cost of the merge operation. Expanding this equation generates a recursion tree, revealing exactly how the workload fragments across recursive levels. If we calculate the total operational cost per level, we find a strict uniformity. Whether it's 2 chunks of size n/2 or 4 chunks of size n/4, the row sum of every single level equals exactly n. The tree stops growing when the node size reaches 1. Mathematically, this termination condition simplifies to a total tree height of log base 2 of n. To find the total algorithmic cost, we multiply the work done per level, n, by the total number of levels, log n. We can quickly verify this tree derivation using the master theorem, extracting our variables, a and b both equal 2, and the function of n is simply n. Applying case 2 of the master theorem, n to the power of log base b of a simplifies to n to the power of 1. This perfectly matches our function of n, confirming a tight bound. The recurrence relation shows this n log n bound is a structural property of the algorithm, remaining consistent regardless of how the initial data is ordered. This table provides a definitive profile for merge sort across all possible operational states. Notice a unique quirk in the best case scenario. Even if an array is perfectly sorted from the start, the algorithm's blind recursive halving still forces omega of n log n operations. Merge sort remains a standard for large-scale data because it provides predictable timing and maintains the relative order of duplicate elements. However, the O of n space requirement is a limiting factor for memory-constrained systems that cannot afford to duplicate the dataset in RAM. This leaves us with an engineering challenge. Is it mathematically possible to achieve linear rhythmic time without paying the spatial penalty? By replacing the external merge phase with an internal partitioning technique, we can eliminate the memory overhead entirely, if we are willing to risk mathematical stability. That is the architecture of quicksort.